And I will shut up now.
Hi. So I'm happy to introduce Seshadhri from Santa Cruz University, as well as Amazon's research. And always he has a great take on things and new perspectives. So we're eager to learn. But also Sophia set the bar pretty high. So let's see.
Okay, yeah, I'm not going to do a song and dance routine. I'm sorry. So if that's what you're expecting, this is not going to be as exciting as that. So I'll try. So there's a long title here. But more seriously, when at least I reflect on the fact that I'm an academic, there's usually a lot of luck and good fortune that goes into that, which is why I like to always, in the beginning of my talk, give thanks to my teachers, people who really influenced how my academic career: Manindra Agarwal, Bernard Chazelle, Mike Sachs, Tamara Colden, Ali Pinar. And all of these people have sort of interacted with me directly and taught me. But I'd say probably the biggest influence on my work has been Lehman and Ron, as is the case for many of us. And it was actually when I was asked to give this talk, it was a little unclear what I should talk about, because I could talk about anything that I've been doing, and it would be influenced by Dana in some way or the other. Also, more personally, there have been multiple instances where I, as a junior researcher, I guess now I'm old, but I was young in the past. And as a junior researcher, I had reached out to Dana saying, I have this different proof of something that you have. And it's happened on multiple occasions that she was so generous to then just, invite me to collaborate with her project and sort of enriched my own work. And a lot of the work on subgraph counting started in that way, where, she was so generous with her ideas and actually helped me build my research profile through that. So I'm very grateful to Dana for all the opportunities she's given. And so that would have been a natural thing to talk about. But instead, I'm going to talk about something else. And I'm going to talk about something called the Lehman-Ron theorem. It's a much lesser known result. Now, she has an embarrassment of riches and many great results. And I don't know, raise your hand if you know what this theorem is. OK, good. So of course, and of course, And I'm surprised that Clement, but that's good. But that's great. So this is great. So you don't need to know anything about property testing. All of us are interested in combinatorics in some way or the other. And I hope that you'll take something. If nothing else, you'll know about this really beautiful result. OK, so where does it start? So let's consider the hypercube, which we all know and love. 0, 1 to the d. D is the dimension. And I'm going to treat this as a directed graph, where I direct the edges from smaller sets to larger sets. Right? And so I also have a natural partial order here, where x is less than y, if all the coordinates of x are less than all the coordinates of y, where again, x, an element is basically a d-bit vector. Now, this is sort of one view, the dimension by dimension view. Another view is a level by level view. Right? I can take all the sets or vertices of the hypercube whose Hamming weight is I, those with Hamming weight I plus 1, I plus 2. It gives me levels, and all the edges are going from one side to the next. Right? So this is the hypercube, which we all know and love. And what's also useful to note is these are regular bipartite graphs, right? Because essentially for every vertex here, it has exactly degree d minus I, and for every vertex here, it's in degree and out degree. They're all regular. And because it's regular, by Hall's theorem, that if you look at two sides, there's a matching from the smaller side to the larger side, like a matching that has everything, includes everything in the smaller side. And so if you were to sort of chain these matchings together, from the smaller side, you have a matching to this side, and this has a matching to this, so on and so forth, you get something called a symmetric chain decomposition, right? You can basically decompose, you get a collection of paths, which are all vertex disjoint, which cover all the vertices of the hypercube. So this is sort of a classic combinatorics, theorem or statement. So let me tell you what the Lehman-Ron theorem is. So what Lehman and Ron proved in 2001 is, so consider two levels of the hypercube and take two subsets, S and T. So S is a subset of a level, and T is a subset of a larger level further down, such that there is so this phi is a bijection between them. So it's just a matching between them, where S is less than phi of S, right, according to the partial order. Right? Does this make sense? So you have two sets, contained in sub-level sets, and you have this matching between them according to the natural partial order. So what Lehman and Ron proved is this really beautiful theorem. They said that in this case, there exist S vertex disjoint paths from S to T. So there exist these vertex disjoint chains that go from S to T. All you need is the fact that S is matched to T at a distance, and you can kind of find these paths. So if you have nothing else, if you just know this statement, you've gotten most of what you need from this talk, yeah? So, okay, so there's a partial order of the Boolean hypercube. And so the bijection just says that for every element here, there's there's something over here that's larger than it, and there's a matching between that. There's a okay, let me say it formally. There's a bijection from S to T such that for all little s in the set, S is less than phi of S. This is true. Now, these paths might not respect that bijection. This is just saying that you get S paths where S is equal to T. So you can basically route from here to here. Except you might not get exactly the bijection that you want, and they actually show that you cannot. They have an example, counterexample. By any distance, this could be anything. You may have comparability which is not given by phi. Like maybe there's something here which is comparable to everything there, and something here is only comparable to one thing. So there's no constraint whatsoever on what the comparability is, as long as you just have some sort of bijection. Yes?
For this, or would this also be true for general cosines?
Great question. For this, you need the hypercube. There are generalizations to certain product structures. But in general, you wouldn't, I mean, defining levels itself needs some kind of product structure, or it's not clear, right? I mean, you have to have some way of defining levels.
So if it's graded, it's okay.
If it's what?
Because if you could have like all bunch of vertices on one layer, then one layer it's one vertex, and then a bunch of vertices.
Okay.
Yes.
Makes sense.
You could have bottlenecks in the middle, right? So you need these. It's not just enough that it's layered. The hypercube plays a very strong role in this. Okay, so this is, I mean, it's truly is like a work of art. It's a beautiful result. So now you know this. I can end my talk and go. But anyway, so let's. So just, as I said, it's a fundamental theory about the hypercube. Just to sort of tell you why it's sort of magical. I mean, as I said, like, by Hall's theorem, we know that between one level and the next, there's a regular bipartite graph. Suppose this level was smaller than this level, then you know that there's actually a perfect matching. There's some matching from S to here, but this isn't necessarily unique. Maybe there's a matching to a different set. So there are probably multiple different possibilities of how you can match S to the next level. And some way you can actually chain all of these together to get all the way to T, regardless of what T is, as long as T is, has this sort of comparability matching. It's kind of incredible if you think about it. Any questions about the statement? That's a nice statement, right? Hopefully. Okay, so I have your attention. And yeah, so what the Lehman-Ron theorem says that there exists capital S vertex disjoint paths, and of course S is equal to T because you have this bijection phi. So what I'll tell you is sort of a new proof for this fact. The proof is, so the Lehman-Ron proof is not that difficult. It's about 1.5 pages, and it uses max-flow min-cut. And we're going to show a different proof, which is, it seems a little convoluted, and then I'll tell you why it's interesting. So consider a minimal counterexample to the Lehman-Ron theorem. By max-flow min-cut, or by Menger's theorem, this minimal counterexample will have a cut of size S minus 1. Right? It's like the minimal counter, because if it was even less than S minus 1, you could even reduce S and T. So make S and T the smallest possible with a counterexample. And so I've drawn this cut in red. Now what I'm going to do is I'm going to use duality and complementary slackness. So bear with me. So we know that every flow saturates this cut. Basically, what this means is there exist S-1 vertex disjoint paths from S to T that saturate this cut. Basically, it says there are exactly S-1 paths that go from S to T such that each cut vertex participates in exactly one path. Okay, this holds by duality and complementary slackness. Okay, does that make sense? Right, so you have these S-1 vertices, and you have this one path. You have these vertex disjoint paths. I should say vertex, right? These paths are special because, again, I repeat, they pass through the cut exactly once. So think of like when you have an ST cut, you have the S side, a cut, and the T side. And these paths will basically exit this exactly once. You could have paths that kind of go in and out of the S side, but these paths are special. Okay. And then you have this sort of, because it's a counterexample, there's this one single vertex that doesn't participate in these paths. This unfortunate singleton that's left behind. Okay, so far so good. Okay, any questions? Okay, so the plan is, I call this the inchworm plan. So we're going to focus on the graph that is formed by the union of all ST paths, because that's the only thing that we really care about. Ignore everything else. Start from this vertex little s, which is on the S side and doesn't lie on these paths, because we know something like that exists because it's a counterexample. Now I'm going to come up with some procedure and discover a point x1 in the next level, which is also on the S side and not on these paths. Using that, I'm going to discover a vertex x2 in the next level, which is again on the S side of the cut in that yellow part, which is not on these paths. And I'm going to sort of keep doing that. And if I finally get here, I have a contradiction. Why? Because every vertex here is connected to some vertex here, right? I'm only looking at the graph formed by the union of ST paths. And at this point, I have a contradiction because the cut should have separated all paths or cut all paths. Yeah, questions? So far, so good? Okay. Either everybody understands or nobody understands. And I don't know which one I'm in. Yes. I'm going to show you how to do that. So this is the proof strategy is going to show you how you can find such a vertex. And it's the discovery of that which is the heart of the proof. Okay, so how am I going to do this? Okay, so S has some neighbor in the next level, like in this collection of paths. So look at that neighbor. If this vertex here is not on the paths, then I'm done. At least I've made one step progress, right? So suppose not. So what happens is when I look at this neighbor, it ends up being on the path itself, right? So what happens is, now here's a question. What did the adversary tell this little vertex S? It said, this pair will lead you nowhere. Okay. So I'll wait for it to sink in. Okay. So right, this pair, well, ended up on these paths. And so I'm just going to use this for an I-dimensional projection because this is according to some dimension of the I. So far, everything has been on graphs. Now I'm going to use the hypercube. This is some I-dimensional edge, right? So I've projected in the ith dimension, gone to the next level. I'm going to just follow this path one step. So this is an edge of the path that I've followed. And then, now this I coordinate was 0. The I coordinate here is 1. The I coordinate here is 1. So I'm going to project back down just to see what I get. And this edge can also project down, right? Because this is a hypercube. This is where the product structure is being used. So I know that this vertex that I've discovered here is a neighbor of S. If it was outside these paths, then again, I have victory. Right? So I projected in some dimension, followed the edge of this path, projected back down. And if I found something that was not on these paths, I've won. So the problem is, the path didn't go anywhere. It actually took me back to these paths. Yeah, so far so good. So what I'm now going to do is I'm going to follow this thing backwards. And I'm going to play this game again. I'm going to project up again. Again, if I projected and I ended up outside these paths, I win. Otherwise, I bump up to that. I go back there. And I project down. And again, I could, if I find something that goes outside, victory. So my problem is every time I project down, I go back onto these paths. But observe that I'm always taking matchings. These projections are a perfect matching. These paths are all matchings. So essentially, once you start from S, you'll actually never discover any vertex again. You'll end up on this path, and this path has to terminate somewhere. And that termination point will be your victory. This sort of kind of makes sense. Essentially, this is the argument. I have to then make it formal using all the properties of the paths. But what this will say is I will get to some vertex on the next level, which is on the S side and not on the paths. I'm going to keep doing this. Okay. Okay, so now what I'm going to do is I'm going to take about maybe 5-7 minutes and formalize this more, like do it a little bit more formally. Because right now, this is sort of a procedural idea. Any questions at this point? All right, so now just to back a bit. That's way too much. Right, so I had to do this process sort of inductively. What I showed you was sort of how to get one step. Let me actually do sort of the proper induction to show how we go from one level to the next level. Okay, so let's go through all of those. Okay, I'm going to start with some vertex at some level, which is on the S side, but not on the paths. So some X. And for contradiction, I'm going to assume that every further vertex I see, which is on the S side, must be on the path. Right? And then using this, I'm going to basically engineer my contradiction. So what this says is, just to be clear, if I find any vertex with either is on the cut or on the S side, after this point, it must participate in one of those paths, those complementary slackness paths. So I'm going to collect all the vertices in this level, which are on the S side, such that their I coordinate is 0, where I is basically, if I look at any X, there's some I dimensional projection I can take. So I'm going to collect all the vertices here. Some of these will lie on the path, some of these don't. But I know that there's this one vertex X that does not lie on these paths. I'm just going to collect all the vertices whose I coordinate is 0 and are on the S side. Some set here, it's non-empty. I'm going to project up along this I dimension. So I project along the I dimension, I get some set. Okay, so why have I colored it this way? Nothing here can be on the T side, because otherwise I'd violate the fact that it's, I've separated. So every vertex that I've projected to is either on the S side or it's a cut vertex, which is in red. And what I've assumed is that now every vertex here must participate on one of those paths, and those paths are all vertex disjoint. So I'm going to follow those paths, just one step, and I get a set B, which is now on this level. Okay. So at this point, just to be clear, the size of A is equal to the size of the projection, because there's a perfect matching. And the size of the projection is equal to B, because again, this forms a matching. Those paths were all vertex disjoint. And then you can kind of guess, I'm going to now project this back down, and I'm going to get the projection of B, which is now a set over here. Right? So I started from here, I projected there, I went there, then I projected back down. Now observe that every edge over here can be projected down here. So every vertex in here, in the projection of B, is a neighbor of some vertex in A. And because it's a neighbor of some vertex in A, it cannot be on the T side of the cut. So all these vertices either are cut or they're on the S side of the cut. So the idea is that I'm sort of stuck basically on the S side of the cut. Okay. So this is sort of the picture that I have right here. And now I can basically complete the path or the argument, whatever you call it. So remember, we said that every vertex on the S side or the cut must participate in one of those paths because they're after this level that we have here. So I can follow those paths backwards from here. So now here's sort of the punchline. Remember, all of these paths were special. They can cross through the cut exactly once. So if I start from a cut vertex and go back, I must go back to the S side. If I started from the S side and went back, I must still remain in the S side because those paths can only cross once. So which means all these vertices here, when I follow those paths back, have to go back to the S side. But if they go back to the S side, they have to go back into here. But there's one vertex here that doesn't participate in any path. So that's a contradiction. All of these sets are the same size. There's each vertex here has one path going backwards. They're all vertex disjoint. A vertex here can participate in at most one path. And there's one vertex that participates in 0 paths. So that's the contradiction. Okay, so all of these paths over here go back to the S side. So you have A paths that are going from this set backwards, but X has no paths on it. So the set has at most A minus 1 paths through A, and that's your contradiction. Okay, so people are glazing off. Don't worry, this is the end of the technical part. But the main point note is that this assumption by contradiction is false. So there must be a further vertex on the S side, which is not on the paths. There's some vertex over here on the S side, not on the paths. And I keep repeating this argument. I get to the end. Okay, so, all right. So maybe I've lost some of you, but you can wake up now because now what I'm going to talk about is something that will not be that difficult to sort of, there are no more technical details. Well, not as much. Yes.
The next layer, you have the same exact structure.
You basically, inductively, you have this property, right? So you are on the S side and not on the paths. So that's all you need. So it's like you have these paths by complementary slackness. And I can go from one level to the next level to find a vertex that is not on the paths, but still on the S side of the cut. And somehow the fact that you could just initiate this process is enough for it to continue. So actually, I was going to give Dana a birthday gift, which is like, I have the proof written up here. I was going to wrap it and hand it to her. Because actually, the real birthday gift, well, which is not just the proof, is we can prove something surprisingly interesting. So take S and T just as before, right? S and T are matched. Suppose they're not neighbors. Their distance is at least 1, strictly more than 1. Right? So let me say an LR solution is a set of vertex disjoint paths from S to T. We can prove there are actually 2 edge disjoint LR solutions, not just 1. So I can actually find 2 different LR solutions which are mutually edge disjoint. Using this proof, you have to be a little careful. That's kind of really, I don't know, I found it really surprising that is true. That actually when the distance is 2 or more, there are actually 2 edge disjoint solutions. And we have the generalized LR conjecture, which is maybe the real gift, is that suppose the distance between this is R or more, then there exists R edge disjoint LR solutions. We can only show R is equal to 2. Okay, so this is this conjecture that we have. I can phrase this in terms of flows. What this basically says is that, again, if you take these 2 sets, set up a flow problem where the edge capacities are 1 and the vertex capacities are R, then there is actually a flow of R times S. It's equivalent to the previous thing by like integrality of flow. Okay, so at this point, you're probably thinking, why? Like, why am I doing all of this? And there's actually a reason. I call it a story of success, as well as a story of great failure. So let me start with the success, and then I'll tell you about the failure. Okay, so monotonicity testing. So there's this classic paper of Goldreich, Goldwasser, Lehman and Ron, and then Samorodnitsky, which talks about this problem of monotonicity testing. So a monotone function is one where if x is less than y, then f of x is less than equal to f of y. So consider Boolean functions. So if I draw the hypercube this way, then a monotone set is something that's sort of upward closed. And the problem is, given epsilon, you want to distinguish a monotone function from one that is far from monotone. Right? And this was like, the big question is like, what is the non-adaptive complexity of monotonicity testing? And I'll spare you through a lot of the like more details of the problem. Even the definition of the problem is not that important. What's more important is really the stable over here. So the original, the seminal result of of Goldreich, Goldwasser, Lehman, Ron, and Samardinitsky show that there's an O of D time tester. I'm not giving the dependence on epsilon here. And the core proof is about 2 pages long. Like the main argument I could present in about half an hour. And it was open whether you could go beyond that. Could you get little O of D monotonicity testers for the setting? And we were able to get this sort of D to the 7/8 to make them D to the 5/6 bound with about 8-9 pages of work. And it was still open whether you could improve that. And then there was this breakthrough result of Kote-Minzer and Safra that got a root T tester. It's about 30 pages of pretty hard work. And it's a beautiful paper, but it's inscrutable, not in that it's badly, it's actually written very well, but it feels like miracle after miracle keep happening in that paper. And at some point you read it and you're like, okay, I mean, yes, this is true, but why, what is going on here? And where does Lehman-Ron enter all of this story? So it turns out that each of these come from something called a directed isoperimetric theorem. So I have a talk tomorrow, which I'll talk about. What's more important is to get from D to little o of D. The Lehman-Ron theorem was central to proving what's called a directed Margulis statement. So that statement on vertex disjoint paths was the central ingredient into actually going from D to that improvement. And it basically has a nice combinatorial proof. And what we thought was that the generalized Lehman-Ron theorem that I said could actually be used to prove the directed Talleyrand. So that's why we sort of got into that whole thing. And I have, about 5 minutes left? Is that correct? So let me tell you more about this in 5 minutes. So it turns out that each of these directed isoperimetric theorem statements, whatever they are, turns out to be equivalent to some hypercube flow problem. So the Poincaré statement, which gives that O of D tester, is basically asking about flows on the hypercube where you only have edge capacities. This improvement of Margulis is talking about a strengthening of Poincaré with some vertex capacity flow. And the Talleyrand theorem is really like a simultaneous edge and vertex capacity problem. So I can tell you what these problems are. And these are just combinatorial problems about flows on the hypercube. It's 2 sets, like sort of with this sort of bijection. I have some flow constraint, like capacity constraint, and I'm asking for how much flow I can send. I put this sort of squiggly equal to because they're not exactly equivalent. They sort of smell or look like the same thing. In some cases, we can prove they're equivalent. In some cases, we cannot. I'm going to spare you some of the details of this, but basically what a lot of the seminal work in monotonicity testing said was if you have a function that is far from monotone, then you can construct these sets of ones and sets of zeros such that there is a matching between them of this form where S is less than phi of S. So these are large sets. And these exist because the function is far from monotone. And what we can show is that basically, if you can show the existence of specific kinds of flows between them, you start getting better and better monotonicity testers. So that's sort of where this story came from. So Lehman and Ron was talking about routing when the sets are in the same level. Here you have sets that span multiple levels, but it seems like some kind of combination of these. Again, I said it seems like because we think, we're not sure. And this is a bit technical, but just, there are multiple sets. Pick the sets that are closest to each other. Pick the sets that minimize the average distance. So it turns out the directed Poincaré is exactly this. The GGLRS is equivalent to saying, I can send ST flow where edge capacities are 1. So I have 2 sets, S and T, with the sort of matching between them. I can send, I can send S units of flow when the edge capacities are 1. The Margulis statement is a bit more subtle. What it says is, if the average distance between these sets is R, then I can actually send R times S units of flow with edge capacity is 1. And with vertex capacity is 1, I can send S over R units of flow. So there's some trade-off between how much you can send vertex congestion or edge congestion. And what the Talleyrand theorem seems to say, I say seems to say because it looks like it's like that, it says that if edge capacities are 1 and vertex capacities are r squared, then you can send r times s units of flow. So you might wonder, where is the square and what all of this is coming from? Ask me later and I can tell you. But it's just, the reason we want to do this is because the proof of directed telegram was so difficult and we had no intuition that we wanted to come up with some combinatorial intuition. And this is how far we got. So we thought that this generalized Lehman-Ron statement could prove the directed telegram theorem. We thought that we could prove this generalized Lehman-Ron statement. We failed on both counts. So all of that stuff that I showed you, I don't know how to show. All we can show is that we can send those two, disjoint solutions. Going back to this question, the Lehman-Ron statements seem to be more flexible for like hypergrids and other product structures, which is why we wanted to prove it. But in the end, I'm just going to leave you with this conjecture. It seems like a cute combinatorial conjecture, which I do not know how to prove, which says that if you have these two sets which are distance r apart, if your edge capacity is 1 and vertex capacity is r, you can send r times s units of flow. We have this proof here that you can do r is equal to 2. We've solved, which I was going to wrap and give to Dana. But I'm just going to end with thanks to Dana for all the intellectual light that she has given.
Any question for Sesh?
Is root D the right bound, or are there?
Sorry?
Is root D the
Your
right
root D is the optimal bound for non-adaptive testers.
Any other question? No, I'm going to use that as a great segue because there's an open problem session during WoLA. So please keep your open problems and give them there. We're going to collect them. And yeah, so let's thank Sesh again.